Good afternoon, everyone. I hope you are doing good and enjoying your weekend. It has been few days since a couple of students they contacted me online about teaching computational complexity course or helping them out for computational complexity. And I promised them that okay, guys, I'm gonna do something. I'm gonna put some lectures in that subject area. Hopefully that's gonna be benefiting to you as well as millions of other students around the world. So this is gonna be so a very short introduction about computational complexity. What does it mean, and what sort of things are being taught in that subject. Basic introduction to computational complexity subject area. Essentially, what when we design algorithms, we talk about time, how much runtime it's going to take. Those So I discussed about time complexity and space complexity in one of previous video lectures under algorithms lecture series. Those who are not familiar with time complexity or runtime about computer programs or algorithms, I would recommend you to watch some initial lectures under algorithms lecture series. So I was talking about the time complexity. So programmers or individuals, you're at a school, you're concerned that how much time my algorithm will take to give me the result, or how much time the machine will take to give you the result. So when we were talking in terms of algorithms, think about we were talking in terms of bigger objects, a bigger picture. Okay, but definitely we are concerned how much time this machine is going to take. We also talk about space complexity, how much memory area this machine going to take to produce certain outputs. Also, we are concerned with the efficiency. We are also concerned with the randomness, whether is there any way we can make use of randomness, pseudo random numbers and whatnot. Also, there is a certain aspects about communication theory. Say for example, um, your friend is living in China and you are living in United States, and you are transferring the information. So what are the minimum, how should I say, what are the minimum words uh, you should exchange with each other so that you can communicate whole message properly? So the sort of communication theory, other aspects like P&P, unsolvability, solvability, whether we can compute certain problems in deterministic time or not. So all those things lump sum, you can add more variables to it, but that sort of thing indicates us to lead to the area of computational complexity, right? So as you say, the complexity word, it looks from outside is sort of complexity, but the essential nature of this subject is not really complex. It is the way how this subject is being designed, or people have written books in terms of mathematical notations, which may sound a bit complex, where in mathematics typically we are looking to find the proofs. Remember, proofs of certain things, proofs of theorem, proof of lemma. So same ways mathematicians, they sit together and they created this subject and used bunch of notations, mathematical notations, which you may feel that course is complex. But in fact, if you understand those notations, it becomes very simple at a different level how we understand things. So for example, think about a problem. Think about that you need to invite some guests at your home. Those may be your friends. and you are such a nice guy that you have friendship with the different people, different group of people, and it is possible that you are a friend of two different people who are enemy to each other, right? So in this particular function, you don't want to invite two such people who are enemy to each other or who cannot see or live together, that sort of thing. Now, what are total combinations gonna be of, and how you're gonna find out? So if your friend circle is, say, small, 4 or 5 friends or 6 friends, you can easily say, you can do permutation combination. But think about your friend circle is bigger, say 100 people, 100 people, right? How much time is gonna take? Okay, so think about your friend circle is 100. So how much time is going to take if you just approach the brute force strategy? So brute force strategy will take typically 2 to the power n number of steps. Now what is 2 to the power n? N is the number of steps, or say let's say the edges. I will commit to later, but in other terms, you can think about 2 to the power 100 permutation combinations you might have to solve in a worst case brute force situation. Think about, you may not, even a supercomputer you use, you may not solve all those combinations. It's a complex problem depending upon your input size, right? So is there any efficient algorithm to do this task? Think about it. Another interesting thing, can your algorithm use randomness to speed up computation? Okay. For example, say we have seen quicksort algorithm when I was discussing about quicksort algorithm, and then when we introduced the randomness, how to select which cell in the array to pick up. So we use a pseudo random number, or how we use a certain kind of randomness, and it improved our runtime. Is there, so for example, you design some algorithm, is there any way you can make use of randomness in computation, and to which degree? Okay, think about this question. Another thing to think about, can a hard problem be solved quicker with approximations? Let's say you are dealing with certain NP-hard problem. We'll come to NP-hard later, but for now just consider certain problems cannot be solvable in polynomial time. So there are different classes of problems. So what if we use some certain kind of approximations? Can we use those problems? Or can we use quantum mechanical properties of universe to solve hard problems faster? For example, scientists are trying to develop quantum computer where information is represented not only by 1 and 0, but it's a triplet, which they call it qubits, the overlapping of 1 and 0. So if they do that, it's gonna say now your computation dependent on 2 to the power something, then it will be dependent on 3 to the power something. Can it be done? What sorts of algorithms would be needed there? What sort of complexity, runtime or space complexity would be needed if we're gonna have a working quantum computer in future, for example? So those sort of research problems. Another important question comes to your mind, your guys' mind. Why do I need to study this subject? Is there any use for computationally hard problems? As a programmer, as a layman, you don't need anything. But think about, if you want to design a machine, if you want to come up with a better solution, you need to be aware of what is underlying theoretical principles. For example, engineers build up machines using the theories which were developed in physics, right? in the same way. So computational theory is the basic foundational theoretical subject in computer science area, right? So those who are passionate about learning, want to go into research field and whatnot, it's always a good idea to have theoretical framework which gives you insight about how the machine is doing computation. That's the main objective of this course, right? So mainly think about this course. Computational complexity is something that where you as a scientist is more interested in knowing what problems can be solved, what problems cannot be solved, what problems can I transpose to some other problem which can be solved in linear time. All those sorts of questions, sorts of mathematical proofs, those are being taught in this subject. So don't be afraid about this subject, it's just a beautiful subject. Just pay attention to mathematical notations and fix the bigger picture in your mind. When you are writing a mathematical notation, visualize the picture, what is underlying scenario behind this mathematical equation, and it's an easy subject. Another thing here to talk about P versus NP. You might have heard this this in a question many times, or on internet search whatnot. Do we have equality of P equal to NP, or P is not equal to NP? Or in other words, I can easily check whether the solution of a certain problem is correct, but it is difficult. It is not as easy to solve the problem in itself. Okay. So if I can find out the answer of this question, I can get $1 million prize. So think about if you can find out a solution to this problem P equal to NP, you can get $1 million. But think about all those problems. Don't jump into you're gonna get $1 million. No, it's just the prize is there to encourage people in terms of research. The monetary value of prize is basically nil. Think about a scientist is investing 10-15 years of their life working on a certain problem. Is that the real compensation, $1 million for their 16 years of their life or 20 years of their life? No, definitely not. But these things are there to encourage people. All right. So I hope you're gonna enjoy this subject. So let's talk about some basic things. Basic computational model. So age-old Turing model of computation, which is being taught since many years, since the origin of the Turing machine model. It's a simple model, but modern days your programming languages, they do that job. So you don't basically see in reality that model is there, but in principle your computer is built up on that Turing machine model. Okay. So what it is, in simple sense, this model is very simple. You have a infinite long tape on which certain symbols are printed. Now you have a some sort of a reading or a scanner which you put onto this on a cell on tape, and you read the value, and based on that value either you move right or you move left or you stay in that position. Okay, and you can represent it like as a sort of control. You have a control which is making this head on the tape to move forward right direction, or to move backward left direction, or to stay in that same position as stay, and store all those states or other information on a working area. In terms of machine, you store the information in state registers. Okay, that okay, I am in that particular stage, that you may denote this particular stage as Q0, that in Q0 state You may denote this stage as Q0, and in this Q0 state, what are the symbols on the tape? Being read is 0, that is the symbol on the tape being read. And what should I do after reading this tape? Should I move right, should I move left, or should I stay? Let's say I move right. And what should I output? Should I output 0, should I output 1, or should I output null? Let's say I output 0 because I read 0, for example. Okay, and then I move to the next state. Okay, Q1. So this whole information of the state Q1 is stored in a state register. A simple computational model. Okay, so it might be more easier to understand for the people who are into electronics, digital design and all. They design the hardware. There is a state machine, and then there is a memory element, and then there is a computational element. Okay, so the computational element is simply is an analogy with the head of the tape. It's reading the input. Okay, and it's a state machine control, or your state machine or your program, which is controlling the head based on the input read and taking the decision, storing in which state I was, what I was doing on some working area or state registers, right? So that's the basic computational model. So always remember, when you deal with any kind of computational machine, always visualize this model. That's what is happening. Now there are variants of this model, multiple head Turing machine, for example, somebody proposed, and how does the computation will happen in that situation. So all those sorts of questions, theoretical framework is basically the objective of this course, right? Now, before moving forward, we need to understand some conventions for for writing and noting things. Now here we study complexity of computing a function. Always remember, we talk in terms of function when we are dealing in the theory. A function f, okay, which takes certain input and produces certain output. So x is finite strings of bits 0, 1, 0. Now think about, you may have say alphabet A, but again this alphabet A is represented using binary strings, encoded strings, right? And it produces certain string or output. It might produce 1, 0, 1, 0, or it just can produce 1 or 0. So it depends, but again it will be a function of some kind. Now 0, 1 to the power n, when we write this way, it means that set of all strings of length n. And if we write 0, 1 within curly braces to the power asterisk, it means all strings, set of all strings. And xy, it's a ordered pair consisting of x and y. X, y, okay, in some order. X, y are in some order basically. Same way x, y, z is a triplet in some order. Same way you can define 4, 5 tuple, or more. Now decision problem or languages, we use these terms interchangeably. Okay, so what it is actually, the decision problem is a set, or languages is a set, okay, which maps is a set of all Boolean functions. Okay, or in other words, a special case of Boolean function. Boolean function is a function which takes set of string or a string of 1 and 0, or f of x, x is a string of 1 and 0, and produces a single bit, either 1 or either 0, just one bit, single bit. So decision problems is a set of all those functions basically. Okay. Now computational problem of computing x, okay, is a problem that where we decide that is there any function which can compute or produce the Boolean output based on the input is x, and what are the set of all those functions means, or language or decision problems that the x belongs to L. LF means the set of all those functions. Okay. Now for example, the dinner party example which we were discussing earlier, say that was a simple example that you can represent that example by a graph, okay, where let's say you have friend Sam, okay, you have friend Alicia, and Sam and Alicia, they do not go together, okay, and here is Ron, okay. Now Ron, Sam doesn't have any problem, Ron, Alicia doesn't have any problem, but Sam and Alicia has problem. So what's going to happen? You're not going to invite Sam and Alicia to your party, you will only invite Ron, okay. So this was the very simple example of a graph where you have just three, three nodes and one edge, or three friends. But think about 100 or bigger number. So how we can translate this problem, dinner party example, that we can represent guests by vertices of a graph and an edge between vertices if two guests or two of your friends, they don't stand each other. Now this becomes a computational problem of finding maximum sized independent set. Remember this, maximum sized independent set. So in this we found that only one element in this set, that is Ron, okay, which is not joining with Sam and Alicia, because Sam and Alicia, they don't they don't stand together, so you don't want to invite them, okay. Now this whole thing what we said in words, we can represent in one line, okay, in a mathematical form. The independent set will be the set from the ordered pair of G, K, okay, as V vertices belongs to vertices of this graph G, and all the edges K for all U and V, that is the pair of vertices, belongs to S, such that this set will not contain any edge, okay. So set of vertices not containing any edge, right. So that we need to find, that becomes our independent set. So that means that we can only invite that many people to our party which are in independent set, right. Now big O notation, we discussed this big O notation when I was discussing about time complexity, space complexity, and under algorithms lecture series. So those who haven't watched that, I would recommend you to watch. Big O notation gives upper bound on your how much maximum time or number of steps your algorithm will take to give you the result. So that's the big O notation. We have upper bound, average case bound, lower bound. All right. So we discussed that. So those are certain conventions. Just remember those conventions. It's a mathematical way of dealing things. We are dealing a theoretical subject. So, no. Okay. So let's go forward. Now, if f is the function which takes a string of bits, okay, and the string of bits are the member of the set 0 and 1. So it's like any, you can have where longer string of bits, but everything is represented by 0 and 1 string, and output is either 0 or either 1. So your function, you have such function f. Okay, now an algorithm for computing this function f, it will be, or it is a set of mechanical rules. Okay, so if we follow those set of mechanical rules, we can compute the function f(x), right? Now those are simple mechanical rules, like read a bit of input. Okay, now your input is in the form of a string 1 0 1 1 1 1. So you just read one bit at a time and read bits from memory or work area. Okay, bits from memory or work area. So we have, in the previous figure we saw that we have given a certain area, work area, okay, or we have stored this information. What we need to do in another tape or a memory. Okay, so we read bits from this work area based on the values which we read from the input. Okay, now we write another a bit to the work area. So after after reading certain bit from this work area, now we know that we read this bit from the input. Now we can write either 0 or either 1 on our work area. Okay, or step number 4 would be, next step would be, either we can stop or put the output. So this is, say, output tape or the output area. We can either put 0 or 1, or we can just simply halt or choose a new rule from our work area, okay, which will be applied for the next symbol, right? So that's simple for 4 steps. If we follow these 4 steps, we can compute this function f(x). So remember, algorithm gives a bigger picture to solve a problem. Now we are at a level of 1 and 0, at a machine level. Okay, so how machine gonna do that? You see, you might have read the architecture of computer. There is a arithmetic logic unit, there is a control unit, and there are registers, right? So what happens that your control unit, it decides what to do. It reads from the memory. There is some computation is being done in ALU. It reads back, it outputs some result, and then it stores that state onto the memory. Okay, so it's a bigger picture of the simple thing what we are talking here. but 4 steps, 4 major steps: read, and then read from the memory or work area depending upon the inputs you read, and then write onto the work area whatever decision you want to take, 1 or 0. Okay, and then next would be either you stop it or output something. Now finally, the running time, how much time machine will take to compute the function f(x) would be simply how many times these steps are being performed. Okay, so a number of these steps being performed, basic mechanical set of rules. Good, it's just the same approach putting in different words. Okay, so now let's go back to our previous example. So we are trying to define a Turing machine. Okay, so Turing machine, see, we have seen in our tape example, there was an input tape, there was a head, control unit, state registers. Now extend that concept. Let's say we have 3 tapes. Okay, our input tape is infinitely long, our work tape we have special symbols which indicates the start of the tape and the end of the tape, and same way our output tape also has special symbols along with 101010, which tells us that this is the starting point and this is the end point. Okay, so let's assume we have one head, and this head can read from the input tape, read only. Okay, it can read and write onto the working tape or our work area, and it can write onto the output tape, okay, or output area. And we have state registers where we store the states, say in which state our machine would be, Q1, Q2 and whatnot. Okay, so this is a fairly simple model of this machine. Now how we can say what is the Turing machine of this model? We can define the Turing machine by this tuple, gamma, q and delta. Okay, so what is the gamma? Gamma is simply, don't get confused too much, it's an alphabet. Alphabet is nothing but what are the symbols your machine, your simple machine can understand. So it can understand, read or write 1 and 0, okay, as well as special symbols triangle and square to indicate square is the end of the working tape, same way end of the tape in terms of working tape and output tape, and triangle is the start. Okay, and the states, Q is nothing but set of states. Okay, so list of all possible states in which this machine M registers can be, including special states start and halt. So, start, special states, and then Q1, Q0 are intermediate states, and halt indicates that is the stop state, machine is halted. Okay, and this halt is interestingly came from Germany. They have in German language halt is, I forgot that particular word, but when I was traveling in Germany, that was something like next halt is tally, something like that. So halt came from there, and then English adopted that. So it's interesting, see how the languages evolve. Since we are talking about theory and programming languages, language theory or theory of computation came down to my mind. All right, and then we have this set of states, and we have delta, that is transition function. Okay, so what is the transition function? Now let's say k is nothing but the number of tapes. So here we have 3 tapes, k is 3. So what this transition function is doing? This transition function is simply what it is doing, it is mapping that I am in this Q state and what are the symbols I am reading, okay, either from the work tape or either from the input tape, okay, and then in which state I will be, Q, okay, and then what alphabet I would be outputting, okay, and then LSR, means my head or the head of the machine, it's gonna move right, left, or it will stay in this position, okay. So it's simply a transition function, okay. So that's a formal definition of Turing machine. You can represent it by a tuple, gamma, Q, and delta. And formally we say that if M computes F, it means that it computes function f in time Tn for some function t which maps from natural number to natural number, okay. So it just see the complexity is not in the subject, it's just how we are representing in terms of mathematical notations. So if you are good with maths, you should not have any problem in understanding this subject, all right. Now we were saying that the delta here, okay. So the delta, how we can write in a formal way, if we want to write it, that say delta is a transition function, okay. Now we are in the state Q, okay, and let's say we are reading sigma 1, that is alphabet from the tape 1, sigma 2, alphabet from the tape 2, and sigma 3, alphabet from the tape 3. All right, we have only 3 tapes. If we have k tapes, then we can keep on going up to the sigma k, okay. And this is the transition function delta. We are in state Q, we are reading these symbols from the input tape, and we are going into the new state, which is, let's say, Q tick. And what would be the next new symbol on the input tapes, right? Input tapes, sigma 1 is for input, sigma 2, sigma 1 is say this one, sigma 2 is work tape, and sigma 3 is your output tape, okay. Now we are going in state Q1, and what symbols we do have? We would have symbols on the working tape would be Q2, that's represented by tick, okay, and then sigma 3 output tape symbols, we would have this one, and the Z means LSR. What is the value we're gonna get from LSR? Means that on which side our head gonna move. So G belongs to, and say G belongs to L S R. All right, and this applies for all 3 tapes. So we're gonna keep our convention K, right? Isn't it simple? It's just what we did talk in words, we can represent it in mathematical way, what this sigma transition function is doing. All right, so after building up the concept of our basic Turing machine with 3 tapes here, this is a very basic model, right? Now let's define something called D time, means deterministic time, means D time is nothing but set of all Boolean functions, okay, that can be computable in deterministic time, or time c multiplied by t of n, okay, and t means there is some function of n, okay, and can be any number. For example, n log n, and c is any constant, okay. So if our function, so it's sort of family of or set of all those functions which can be computed in deterministic time. Now we can define our first complexity class of problems, that is P. What is P? P is nothing but the union of all such functions which can be computed in deterministic time for certain constant c, n to the power c. It doesn't mean that you say, okay, n to the power 100 is my P. No, you can't solve n to the power 100 in realistic time. No, it means that you can say, let's say, you know, you go up to the n, typically n square, n to the power cube, and even though if your input is not too huge, you go up to n to the power 5, okay. So we defined one class of problem P. In a layman's term, the P class of problem you can solve by some function in deterministic time, okay. In the next lecture, we will discuss about further classes of problems, P, NP, NP-her, and further complexity classes. So idea of this course or of this subject is not to, you know, be afraid, you know, it's just understand step by step. It's a theoretical base, theoretical background in the theory of computation, how the machine is computing, okay. There is a mechanical way, but that mechanical way can be understand. It is very simple, like English language. You have alphabets, letters, those are like mechanical things. But how to make inference of it? Just out of 26 letters, you have infinite number of words, right? I don't know the whole vocabulary, but you know, the people who are doing research in language, they might be knowing, but just because you have just 26 alphabets, right? In the same way, we are trying to develop or trying to understand the theory, okay. Now here our alphabets are simple. Here in our simple machine model, what alphabets we have? We have the start symbol, we have stop or the end of the tape, and we have 0 and we have 1. So our alphabet here has only these symbols or these letters. That's it. Simple. And we are just, you know, doing so many amazing things our computing machine is doing. All right, guys. So this was a very quick introduction, which I thought that I should be doing to help you guys out to understand the computational complexity subject. So don't get afraid. This is an easy subject. The complexity lies in our mind. So just understand this subject with open-mindedness, and hope you guys you know, enjoy it. If you are struggling with this subject, you may contact us for private coaching, private lessons. And thank you very much for subscribing LeProfesseur YouTube channel. Those who haven't subscribed, we would recommend you to subscribe LeProfesseur YouTube channel. And we appreciate your support, and that helps us to, you know, and gives us encouragement, motivation to create more and educational videos to help millions of students out there in the world. I hope our little effort is beneficial to you. Do send us your comments, to send us what you feel about our lectures. Remember, we use standard textbooks which are being taught at university. We read those and then we prepare these lectures, right? So please do send your comments, feedbacks, that will be very much helpful for us, and please subscribe to LeProfesseur YouTube channel. Thank you very much. Have a wonderful day.